Hello. Today we are discussing electric field and equipotential lines. Now you may have heard from popular movies and comics about electric field where superheroes release electricity from their body. Well, that's not really accurate. Okay, so imagine two objects at a set distance. Now, this is obviously not present under the naked eye, but there is an attraction or interaction between the electrons of the two objects, where they either attract or repel each other. This phenomenon is called the electric force. Now, this is a quantifiable force that can be observed under 2 dimensions or 3 dimensions at any given point with 2 or more objects. Now, the immediate space around the objects where the force or the charge can be experienced, quote unquote, is called the electric field. Now, you might be wondering, Ren, how do we measure electric field? Well, to answer that question, we have to consult with our experiment over here. Now, the goal of this experiment was to explore more on the properties of electric fields, the more important ones being these two. And to do that, we need to start with batteries. Well, actually, we also need these stuff. Basically, in this setup, we wanted to connect an electrode to the positive side of the battery while the other on the negative side. Put them in this orientation, and then we measure certain points of the field using our voltmeter, which is also connected to the battery, by the way. We also added water so that electric signals can be picked up by the voltmeter much easier. Using vertical lines with intervals of 2 from the x-axis, we wanted to plot voltages of 8.5, 7.5, all the way down to 3.5. Repeat this process on every line, and then extrapolate the curves. This curve is our equipotential lines. Now this line is important because this is a gradient vector delta L, whose function is always perpendicular to the level curve proven by this series of equations. Now the point of this experiment is that we can actually get the vector magnitude at any point using delta L. We know that delta V can be expressed as a derivative of V along the perpendicular line L. So, following this equation, we get delta V at each point. And voila! We have our results. 0.71, 0.69, 0.42, and 0.24 volts per centimeter. Further analyzing our results, we can also deduce that areas with higher electric field vectors will also have closer equipotential lines, in turn having dense areas where the electric field is stronger. To conclude this video, we found out that the electric fields can be expressed both as a scalar and a vector field. Electric vector E can be mathematically derived from a potential field V, and that high gradient regions will have equipotential curves closer together and experience stronger electric fields. And cut!